So just remember, we're going to be talking about functions, these things we're going to call complexity or growth functions. We're going to be interested in the asymptotic orders of them. That means that which one grows faster, or if I want to compare two different running times, which one will be more efficient for sufficiently large inputs in certain circumstances. So the way this would get set up, as I've discussed previously in series like my Big O Bootcamp series, which I encourage you to check out if you're curious more about some of that background. Remember, the whole step in this process is that you would identify a type of analysis. Once you have an algorithm, you identify how you want to analyze the algorithm. You formulate what we call a complexity function, and then you derive that by counting operations of the algorithm based on the kind of analysis you're using. Then you come up with, you try to figure out what the relationship it has with respect to big O, or big omega, or big theta, whichever would be most appropriate for your setting. And I must stress that there isn't just one tethered to a kind of analysis. It just depends on what you're trying to describe. So let's define what big O is. So what we're going to do is we're going to let f and g be complexity functions. Complexity functions. So just as a reminder, remember that these are going to be taking in a positive integer, or if you want to be charitable, you can also include 0 in that, so 0 and up. It's going to take in these counting numbers as inputs. They're going to represent, say, the size, if we're talking about algorithmic running times, the size of that input. And then what it's going to do is it spits out a non-negative real number, at least in our definition. So we write f is big O of g if and only if the following is the case. So for those that aren't familiar with this phrase, this if and only if phrase, what it's saying, hi Miss Kitty. So what it's saying is that if I say something like this, like f is big O of g, what it's saying is that whatever follows this is equivalent to me saying that. So if f is big O of g, that means that whatever follows here also has to be true. Likewise, if this is false, that means that f is not big O of g. Okay? So if and only if there exists some positive real constant C. So very often I'll abbreviate this as follows. So very often I'll abbreviate this like this. So C is in the set of all positive real numbers. That's what this says. And a positive integer, n0. So these are both constants. I'll make that clear. Let me just write constant right here. Miss Kitty, what are you doing? What are you doing? You're not supposed to be up here, you funny kitty. Come on, come on, come on, my friend. You're gonna go down. Here you go. She'll be back. So, such that for all n greater or equal to n0, it has to be that the following inequality holds. So f of n is less than or equal to c times g of n. So let me break this down a little further, okay, everybody? So what this is saying is that there exist these two constants, c and n0. And it has to be that this inequality right here has to be satisfied for all values that are n0 or greater. So these are on integers, right? So that means that It has to be, for example, if n0 is 1, for example, then it has to be true for 1, 2, 3, 4, 5, 6, 7, and so on. If n0 is, say, 10, then it has to be true for 10, 11, 12, 13, 14, 15. The point is that this is what we would call an existential statement. So it's saying that there exist these two constants such that this property holds. So the game in town is to identify two constants, but you have to prove that they in fact are going to work. That means that for all n greater or equal to n0, this inequality is satisfied. Is that clear, everybody? So let me show you a picture of what I mean by this. So let me show you. So suppose I give you two functions. So here's a linear function, and here's a quadratic function. I'm not going to get too delicate with this. And Miss Kitty, what do you want, Miss Kitty? Oh, Miss Kitty, you're being silly. You're silly. Behave yourself, okay? I know, she's been a real rascal lately. So suppose I have this quadratic here and this linear function. The details about it aren't terribly important. I encourage you to find just some linear function, some quadratic. It doesn't matter too much for this picture. The point is that this is as I increase the input n, and this is for the output here. So for example, suppose that this is say f, and this is g right here. So the point is that there's going to be some constant multiple of g such that there's going to be a point eventually, n0. Keep in mind, n0 could be that point where they cross each other. Keep in mind, a function may cross multiple times. But the point I'm getting at, the point is that there's going to be some point where this function, this g times some constant multiple, is going to be dominating f. So it's going to dominate f eventually. So for all points after this, because this function will dominate f with this constant multiple, for all values after this. So this is for n0 and later. So keep in mind, n0 could be anywhere along this line on this axis here. So keep in mind, the shape of the function might be a little different. It could be that maybe it beaters up and down a little bit, then starts going up. The point I'm getting at is that there's going to be some point where this happens, such that if I take a constant multiple of g, and keep in mind, you have control, as long as they exist, you have control over c and n0 when you're proving claims like this. So we'll see an example of the sort shortly. So very often when somebody says something like this, the way you would abbreviate or say this is you would say f is big O of g. Sometimes people will say that f is of order g. Keep in mind that you have to be a bit careful when you use big O notation. I'll have more discussion about that when we get to some other asymptotic notations. So likewise, you can also say that f is in big O of g. So you'll find that I'll very often use the first and the third very often when I'm describing things for you, okay? So first thing, I use this phrase in right here as opposed to just is. There's actually a literal meaning for why I'm saying that. It's because when you write big O notation like that, it actually represents a set of complexity functions. So what do I mean by that? So big O notation, represents a set of complexity. Yes, I know, Miss Key. Yeah, it is a set. Is a set of complexity functions. So very often when somebody says the word is, it literally means is in, okay? So very often you'll see when somebody writes this, they'll say f is in, akin to what I just wrote over here where I had some element that is a part of some set So in that case, a number is associated with a number set. Here is a function associated with a set of functions. So very often it's written like this. And we're going to see that with big O, it operates as an asymptotic upper bound. Asymptotic simply meaning there's a sufficiently large value of the input in this case. So sufficiently large, asymptotic upper bound. Sufficiently large input such that it's going to be that a constant multiple of this will dominate the function that is in big O of G. So this is actually a set. So big O of G is a set. So for example, like I discussed a moment ago, when I talk about, say, big O of 1, big O of 1 is actually a set of functions. Here's a picture, for example, of what big O of 1 might look like. It could, for example, have the function for which it outputs 1 every single time. It may have another function for which it outputs the number 2 every single time. It may have another function for which the output is always 100. But there's many more that might be in here. We're going to see that because of the fact that because of the direction of this inequality right here, that it's going to be that they're always going to be successfully nesting in each other. When I give you one order of a function, if there's one for which it will dominate it, it sits either in the same set or it's going to be contained in a larger set. Okay? So just as an example of what I'm talking about here, as we're going to see in one of our examples here, we're going to see an example of a linear function. And a function like that, like n or 2n minus 1, these are going to belong to another set called big O of n. Those are versus this one, which is big O of 1. So they're going to be nested in like this by the orders of these functions. So the order, the asymptotic order. I should be a bit more precise. The asymptotic order of that function. So hopefully that's pretty neat. So remember, it represents a set of functions. Another standard way people write f is big O of G is also this way. Using an equal sign like this. However, I must warn you that this is not an equal sign. At least in the way that this means is. So it's actually saying is. It's not literally saying that f is equal to G. Sorry, big O of G. It's saying that f is big O of G. So you might ask, Dan, why would you use this? It's because very often when we study asymptotic notation like this, it's very often handy for simplifying calculations to have it so that you can operate on it like you're manipulating functions in a part of an algebra. But also you would like to be able to state these things by clumping them together by their asymptotic orders, as in using the big O notation. Just a quick example of what I mean by this. So say, for example, I have 2n squared plus 5. Instead of writing 2n squared, one thing that we can prove using the definition is that 2n squared is actually big O of n squared. Likewise, you can also prove that 5, as I discussed over here, is also big O of 1. So all you do is you look at the order, the asymptotic order of the functions in terms of the big O, and you take the one that's the most dominant in this case because there's a constant number of terms. If that wasn't true, you have to be a bit more careful. And I can just say that that's big O of n squared. This very often comes up if you have an algorithm with multiple steps in it. You may want to analyze parts of the algorithm, then add up all the operations. And after you've done that for each one, then you can bring them all together. So that's a very common usage of the big O notation. The point I'm getting at is that you cannot read this back like this. Because remember, this says this is a set of all of, at least contains all the quadratic functions, but you're going to lose a lot of information when you write big O of n squared. Because remember, like I said, these functions are inside of buckets, but they nest within each other by their asymptotic order. So for example, something like the function n is big O of n squared too, because it's in a bucket that's in of one with a lesser asymptotic order, right? Because it's a linear function, not a quadratic. But you can actually sit down and use this definition to prove that. So you lose that information as soon as you try to like expose that out here. You're gonna lose that information. So it doesn't work like an equality, like it's not, this isn't an equation. What I'm doing is I'm actually doing a shorthand representation of this as big O notation so I can perform very simple calculations. It's meant for simplifying calculations like this. You can be very precise about it, but you have to be careful about this, okay? So anyways, let's chat about this now. So now that I have defined big O notation for you, I think it's important that now we talk about an example. Let's do an example together. So I thought I would pick one of these functions that I have over here on the board. So let's do an example. So let's prove using the definition of big O that 2n minus 1 is big O of n. So let's try proving this together, everybody. So what I was going to suggest is we take that definition that we've written over here, and let's think about it as a game plan. So what was the original game plan? Let's back up over here. So this definition over here had two things you're supposed to find, right? So that's what it says. Remember, it says that f is big O of g if and only if there exists what? There exists what? What does there exist? There exists what? There exists some positive real constant c, a positive integer constant n0, such that for all n greater or equal to n0, that inequality has to be true. So the game plan here is that we need to identify c and n0. And remember, it's a statement about the existence of them. So we have choice over what these are. We have to then, once we pick them, we have to check that this works. A common mistake students make is that they just pick c and n0, which is blindly, and they just test this for a given value of n. That doesn't work. You have to do it, you have to make sure that this inequality works for all n greater or equal to n0. That's the catch. So let's do this together here. So we're going to try proving this using the definition of big O. So remember, the game plan is that we need to find c and n0, and that's what we're going to say at the beginning of our proof together, okay? So we find constants. Constants c, which is a positive real number, and n0, which is a positive integer, such that for all n greater or equal to n0, what was the inequality again? It's f of n is less or equal to c times g of n, right? So f of n is 2n minus 1. Then we have c times whatever is inside of here, right? So it's c times n. So we have to find the two constants. So one tip I can give, and this isn't the only way of doing this, this is just a suggestion. One way to achieve this is by simply picking one of the constants and then deriving the other constant. That's a very common strategy for proving claims involving big O. I find usually picking c first is helpful. But it's not the only way of doing it. It's just a common way of approaching this. So what I was going to suggest is that we try to pick a c that makes sense for us, okay? So I have an idea. So you'll see that I have on my left-hand side of that inequality, do you see how I have 2n minus 1, but it has something that looks like an n right here, right? It has n times a something minus 1. Can I make this look kind of like that so that it makes it easier for me to pick c? Now there's several obvious choices once you get this idea in your head. So let me show you what I mean by this. So if I have, say if I have 2n, that's two things in my bucket. There's two n's in my bucket here, right? Now, I have a minus 1. That's a something, right? Now, keep in mind, that's only negative. It's going to make it smaller. but I'm going to be overly generous. I'll come back to it. And I'm just going to say, okay, that's another term that I could write in terms of n, right? I can replace 1 with n, just imagining this in my head. I would make it, instead of -1, I would make it just n, right? So I have 3 things that I can kind of make look like an n. So I have specifically 2 n's, and I have something that I could write in terms of n if I wanted to. But on the right-hand side, I would like to be able to match these 3 things I can write sort of like n with 3 things that are n. But you'll notice that if I have 2 n's on the left-hand side and 2 n's on the right-hand side, they match each other. And whatever's left, if I include an extra n on this side, it most certainly will be larger or matches whatever's on the left-hand side. So we're going to use this bucketing approach to decide on what to use for C. So is any ideas of what we should pick for C? So keep in mind, there isn't just one answer here. There isn't just one answer here. So what we're going to do is I'm going to pick, just for the sake of simplicity for us, as I mentioned, we can get a little bit smarter about this, but I'm just going to keep it simple. We're going to pick C is equal to 3. So we're going to start off with 3, and my goal is to figure out what n0 should be. So keep in mind, if we don't necessarily have to find the smallest value for n0, it could be any value for n0. Just the catch is that you can't just guess it. You have to prove that that actually works. So it's usually you have to derive that using an argument. So for example, I can't just say n0 is 10,000 and just leave it at that. I actually have to show you that n0 can be 10,000 and it would work. But I'm going to show you an elegant way of arguing this, just to keep it simple for us, because it's our first example. So we're gonna pick C is equal to 3. Then we need to find n0. We need to find n0 so that 2n minus 1 is less than or equal to 3 times n. That's what it means when I put C in, right? So now I have to figure out, just like in my picture I had over here, so now I have 2 linear functions that I'm playing around with, right? I have to figure out where this n0 can be. Now remember, n0 is a positive integer, right? We can't just simply just say, hey, look, I'm just going to make it 0. You can't make it 0 because 0 is not a positive integer. It starts at 1 and goes up. So now I'm going to use my bucketing idea. Observe that 2n minus 1 is less than or equal to 2n plus n. So this is what I was talking about. I'm going to make the minus 1 look like something kind of like n. Now, a mistake I could make is I could make it minus n, but we're going to not do that. We're just going to try to come up with an upper bound on 2n minus 1. So I'm just being very charitable on how I do it. But I want to write it in terms of the function. So in this case, n. So in terms of g. But that's just 3n, right? But my claim is that this actually will work for every n greater or equal to 1. For the following reason. So as you can see, that 2n is less or equal to 2n, right? Like we mentioned with the buckets, right? This is because you could divide both sides of this, you get 1 is less or equal to 1. So this is true for all n greater or equal to 1. And minus 1 is less than or equal to n for all n greater or equal to 1. Right? So you wonder where I get the 1 from. It's because I've taken what's on the left-hand side, I've compared it term by term with what I've written right here. So I take 2n, I compare it against 2n. I take minus 1, I compare it against n. So that's what I'm doing right now. So what I do is, if I could show that each one of these is less than or equal to the right-hand side, then what I do is I sum over these, and I get what I have right here. Does everybody see that? This is what I'm calling the bucketing approach here for you. So let's talk about this. So now I have a reason why this would be the case. So now I know that this will work for all n is greater or equal to 1, right? So I'm going to choose n0 to be 1. Now I must stress that you could have picked n0s 2, 3, 4, 5, 6, 7, could have been 10,000, but notice that the way my argument works is that it seems like 1 is a very natural thing to argue here, right? It's the largest value among these that I have here. So I choose n0 to be equal to 1. Therefore, now I need to make sure I have a conclusion that invokes the definition of big O. Because remember, I'm just saying that we found the constants. I didn't say why we're doing that yet. So I'm going to invoke the definition of big O to conclude our proof. Therefore, by the definition of big O, 2n minus 1 is big O of n. And we're done. So that box there is just to indicate the end of the proof, everybody.